Hi all. In this class we can see what is a parity check matrix and it is represented as H, and in previous class we studied what is a linear block code and what are the matrices we can use for this linear block code. So in that we studied we are using two types of matrix, that is one is a generator matrix, another one is a parity check matrix. And the generator matrix is represented as G and it is used at the channel encoder side, that is used to encode the message, that means that is used to convert k bit message size into n bit code word. So that is the purpose of generator matrix. Next we can see what is a parity check matrix. So the main purpose of this parity check matrix is used at the error correction. That means it is used at the decoder side and it is used to decode the code word, as well as it is used to check whether there is an error or not. If there is an error, we can use this matrix for error correction. We can see what is a parity check matrix H. So we know that we have a generator matrix G having size k by n with k linearly independent rows. So there exists an n minus k by n matrix H with n minus k linearly independent rows such that any vector in the row space of G is orthogonal to the rows of H, and any vector that is orthogonal to the rows of H is in this row space of G. That means this property is saying that G into H transpose should be equal to 0. So that is the relation between this generator matrix and parity check matrix. So we already studied that we have a generator matrix having size k by n. That means there is a k linearly independent rows there exist in the generator matrix. So the corresponding matrix that has n minus k by n matrix size is the parity check matrix, which consists of n minus k linearly independent rows. That means this vector in the row space of G is orthogonal to the row of H, and any vector that is orthogonal to the row of H is in the row space of G. That means G into H transpose should be equal to 0. So that is the parity check matrix. So we can see that if G into H transpose is equal to 0, then we can also write that the C into H transpose should be equal to 0. That thing we need to prove, that we can see in next class. So remember, the relation between this parity check matrix and the generator matrix is that G into H transpose should be equal to 0. Otherwise we can say that the generator code word into H transpose should be equal to 0. So this matrix H is called a parity check matrix of the code. So we can see that the 2 raised to n minus k linear combination of the rows of matrix H form an n by n minus k linear code of this code word vector. So and this code word vectors we can call as dual code of C also. So we can see that this parity check matrix H is mainly used for error correction. So we can see how we can represent this parity check matrix. So we already said that the parity check matrix is notated as capital H, and it has two expressions as like a generator matrix. So if we are representing the generator matrix as matrix of PIK format, then the parity check matrix should be IN minus K P transpose format. So if G, the parity check matrix is first, then followed by this unit matrix, that is identity matrix, then this parity check matrix should be IN minus K followed by P transpose. Or if G is IK followed by P format, that is GS matrix of IK P format, then the parity check matrix H should be P transpose IN minus K format. So remember, if in G P is the first term, then in H the P transpose should be the second term, and if in G P is the second term, then in H the P transpose will be the first term. So that you should remember. So we can represent this H based on the G representation. So here we followed that this G is represented in such a way that I followed by P. So we can represent H here as P transpose followed by IN minus K. And the size of this H matrix, we said that it is n minus k by n. So we can represent represent this parity matrix as P11, P12 up to P1 n minus k. Similarly, the last row is PK1, PK2 up to PK n minus k. So we can represent H as the first row consists of P11, P21, PK1. Then the identity matrix as 1, 0, 0 up to 0. Then the last row of H is P1 n minus k. P2 n minus k up to Pk n minus k, then 0, 0, 0. The last digit is 1 here. It's not 0 for this identity matrix. The last row, the last digit is 1. Here it is represented as 0. That's wrong. Here it is 1. So that's the way we can represent the H matrix. So we need to take the P transpose, then followed by this identity matrix. So we have k columns and n minus k columns are there. So the size of this H matrix is n minus k by n. So mainly this H is used for error correction. So this is the parity check matrix. So this way we can represent a linear block code. So at the encoder side we have the generator matrix, and at the decoder side we have parity check matrix.